Mass versus weight. Mass and weight are not the same thing. There's not a conversion between the two. Despite how it's used in everyday language, despite how businesses might use it, mass and weight are not identical. I remember I was working on a project for a business when I was doing IT consulting, and they wanted to express something in terms of kilograms, and they wanted a conversion factor built into the system to automatically convert from pounds to kilograms. And I said, but that number's not the same. It depends upon where you are on Earth. It does change. And if you're shipping, several tons worth of material, this could make a difference. And they said, oh, we don't care. Well, potentially they could have lost some money, or maybe they cheated their customers. So the big thing is that, for the most part, for right now, my mass is constant. Now I'm inhaling, exhaling. There's going to be some small difference there. Probably skin's going to flake off because where else does dust come from? So, but for the most part, my mass is constant. If I stepped into the transporter beam, which I have next door, then and appeared on the moon, my mass hasn't changed at all. But my weight has. The weight deals with the gravitational pull. I have weight because I'm being pulled down towards the planet. I go to the moon, I'm being pulled towards the center of the moon. My weight changes. My weight here is about 900 newtons. On the moon, it's about 150 newtons. My mass here is about 90 kilograms. My mass on the moon, about 90 kilograms. It's the same. My mass doesn't change. My weight does. They are very different. Now, there is a relationship between them. Weight is equal to the mass times the acceleration due to gravity. Now you look in a textbook under acceleration due to gravity, and they're going to go, some books will say 9.8 meters per second squared. Sometimes they round off and they say, it's close enough to 10 meters per second squared. And some books will go, 9.81 meters per second squared. Well, that is not a constant. The acceleration due to gravity depends upon where you are. And so the world average is 9.81. The Winston-Salem average, and I'm pulling out my notebook, which has this type of information in it, which some say I probably should have done before I started this video, but I didn't, so there. Winston-Salem, the average is 9.795679. I'm trusting they're all significant, but in essence, that is for Winston-Salem. It's not the same everywhere. Charlotte is 9.7975. Columbia, South Carolina, 9.7964. Mount Everest, 9.779. That's sea level. I just have a formula there, so that's not really the right place. So anyway, I don't know how well you can be able to see this. See if I get close enough for you to at least be able to see some of them. And so the acceleration due to gravity changes depending upon where you are. Now, in terms of the Earth, what the gravitational pull, and from which we get the acceleration due to gravity, the gravitational pull depends upon, in essence, how much mass is underneath you, and where is it located, how far away is it. So if I'm at the equator where you got the bulge, then you're farther away from the center than if you're at the North Pole. North Pole, because the Earth is kind of squished this way and stretched out. Go back, stretched out this way, squished this way. The world is not a sphere, it's an oblate spheroid. Also, there's elevations. Top of Mount Everest, you're farther away than you are at, the ocean. And so altitude and latitude usually figured into the more complex formulas to try to figure out acceleration due to gravity. So, and why is it called acceleration due to gravity? Because if I drop an object there, ignoring air resistance, that is the rate at which it's going to fall. Notice that has nothing to do with the mass. The mass is independent of the acceleration. We talked about in the other video where we dropped the book and the marker. So, mass versus weight.